जी हाँ, वेलकम देवा साहब। जस्ट
ओके,
टाइप
नमस्कार
हो गया, शुरू कर।
सबको सबको मेरी नमस्कार। हम लोग we always say that our USP is the punctuality, but today because of some technical glitch, I am myself 2 minutes late. But anyways, on behalf of the Dr. Dhawan Academy of Geologists, I welcome you all to this edition of our open houses. And we are all cricket lovers in India. So if I speak their language, so I can say that the academy today is hitting a six. We have hit a six because this is the edition six of the open house. And we are lucky to have today Mr. Imran Sayeed, one of leading experts in the country and my dear friend. And uh, I mean, these open houses make us maintain a contact with you all. We come in touch with you every month once. This is our way of being in contact with you. And open houses, as you know, we conduct them. It is a 1 hour program. We have a lead speaker. Today, Mr. Imran Saeed is there. And then you can raise your queries in the chat box. And after the presentation is over, we will respond to the queries. The speaker will respond to the queries, and then we can take some oral questions also if there is some time left. So the topic is very relevant today. It is on tunnel boring machines, and as we all are aware, these days we are having, a full-fledged development going on in the country, particularly in the transport sector. So many tunnels for railways and for roads are being taken up in the Himalayas. So more and more TBMs are coming in. And today we can see what our friend Mr. Imran Saeed has to offer. And I will not take much of your time now. And I will request Dr. Dhawan, because Mr. Saeed has been a very promising young colleague, a colleague of Mr. Dhawan, Dr. Dhawan in NHPC. Right, and I think that an introduction to Mr. Imran Saeed, there is nobody else better than Dr. Dhawan himself. So Dhawan Saab, please, the ball is in your court.
Thank you very much, Deva साहब. Very good afternoon to all the friends, and a very happy Teachers' Day to you all.
Same to you, sir.
This is
Same to
just
you,
a
sir.
coincidence that today's speaker is Mr. Imran Saeed, who is by nature he is a teacher, and this is an honor to him, and honor to the academy also, that we have invited him today for this open house session. As Mr. Deva has said, uh, I'm really very happy to introduce today's speaker, Mr. Imran Saeed, who is a personal friend of mine for the last 3.5 decades. Mr. Saeed is an excellent field geologist with a scientific bent of mind. He studied at Aligarh Muslim University, and after completing his master's in geology and PG diploma in hydrology, he joined NHPC as a professional geologist in 1985. He had served NHPC for about 35 years and goes from a geologist to head of the Geology and Geotechnics division as the Chief General Manager. I had the privilege of working with him for very long stints in the field as well as in our corporate office. While I was in NHPC, I really found him always very dedicated and focused and motivated officer to achieve the desired organizational goals during his service. He had contributed significantly for investigation, planning, and construction of several hydropower projects in the country. Here, Uri Stage 1, Dhauliganga Stage 1, Mangdechu project in Bhutan, and Parvati projects in Himachal Pradesh need a very special mention for his exemplary work as an engineering geologist. His desire to upgrade his professional knowledge is unlimited, which is evident from his academic achievements during his service. He did MPhil from EMU in 1995 and graduate certificate in geotechnics from Missouri University of Science and Technology at Rolla in USA in 2014. And of late, he has completed online training course on backyard meteorology from Harvard University. A very accomplished person. He is the Vice President of International Society of Rock Mechanics India and member of several national and international bodies. He is a member of editorial board of Journal of Engineering Geology, and he himself has written several papers in national and international journals. After his superannuation also, he is working very, very actively as a senior consultant in engineering geology and geotechnics for many infrastructure projects in the country. Over to Mr. Imran Sayeed, please. It's a great pleasure having you today. Thank you very much.
Thank you very much, Dhawan Saab, from the bottom of my heart. Thank you very much, Devaji, for this bestowing this honor upon me to be amongst you in this hard times particularly. And Dhawan Saab, as usual, is doing a great service to the country by bringing in all geotechnical professionals under one platform. Let me share my presentation with you and go to the is it visible?
Not yet, Imran.
Presentation.
It takes a little time sometimes.
Varun, you remove your slide. Varun is sharing it.
Yes. इमरान दोबारा से स्क्रीन शेयर करिए. Oh yes. Now Imran. Yes. Okay.
Yes, visible now.
Now visible.
Yeah. But now go to this slide mode.
Yeah. Today I'm going to speak on ground risk assessment and solutions for TBM tunnels in Himalayas. As you all know, tunnels are having now more and more importance. They have already in hydropower projects, but of late in infrastructure projects in India, particularly the railway and road tunnels, there's a huge amount of tunneling going on. And naturally, when we focus on tunneling, we would like to know the methods through which we can achieve a rapid progress. And one of the very attractive methodology for making tunnels very quickly is a tunnel boring machine, which readily comes to everybody's mind. But we should be aware that TBM has its own pitfalls, has its own ups and downs. We in our own country, particularly in the Himalayas, we have had a mixed type of experience, I should say. We have had phenomenal successes. The success which TBM, when it occurs, is spectacular, really. And when it falls down, literally it gets buried, as happened in some of the projects. So the contents of my talk today are focusing on requirement of TBM, what is Himalayas, what are their intricacies for a geotechnical professional, past experiences I have discussed very briefly, risk assessment and geotechnical baselines, planning. A lot of planning goes into before you decide about the TBM, investigations, testing of course, and solutions based on my own experience, particularly in Parvati open shield TBM. What are the contractual problems which come? How should be the selection of TBM facilities? These things, apart from geology, have a great bearing on the success of a TBM tunneling project. Finally, tunnel boring itself, what kind of support? A line. Requirement of TBM. Long tunnels, TBM should be put only where long tunnels are required and there are no intermediate edits. In hydro projects, they are used for irrigation schemes even where there is an intra-basin transfer of water involved. In cities where cover is less and you don't want to disturb structures on the surface, there is use of TBM.
Something wrong?
Yes, looks like some connectivity problem at his end.
Imran sir? I'll speak to him on telephone.
This is an unusual setback, I think happening for the first time.
वरुण फोन से बात करिए.
मैं कॉल कर लेता हूँ, I will call him.
जी. तब तक हम लोग आपस में कुछ बात कर सकते हैं. मैं अरोड़ा साहब को देख रहा हूँ. धन्यवाद साहब. अरोड़ा साहब आप आए हैं. जी. अरोड़ा साहब इज फॉर्मर डायरेक्टर टेक्निकल ऑफ THDC. संजय कुमार जी को भी देख रहे हैं. प्रभाष पांडे जी हैं.
Imran Sayeed is back.
जी. इमरान सईद इज बैक. ओके. वेलकम इमरान.
He said he's back.
But I can't see.
Yeah, there was a power breakdown.
Okay, no problem. Welcome back.
And, I came back.
Okay. Wonderful. Please continue.
I'm sorry for this. Hold up.
No issue.
No problem.
Now I'm connected through mobile, so even if power goes, it doesn't matter. So long tunnels, in a vast majority of cases, tunneling by TBM is a compulsion rather by choice. Himalayas, as we all know, this is a famous diagram from the net. It started in the outermost part, the Lesser Himalayas, the Great Himalayas. These are the three places where we are having maximum projects. What does it mean to a geotechnical engineer? We say Himalayan geology, very disturbed rocks. What does it mean? I gave a presentation in Geological Society of America where I correlated different Himalayan ranges with typical geotechnical problems. In Shivaliks, for instance, you can expect softer, low-strength rocks. There is less consolidation. They have not undergone all the movements of the Himalayas, so they have fewer structural disturbances. Lesser Himalayas is a gamut of rock types, as we all know, majority of schists and phyllites. Over there, there is a lot of quartzite, a lot of shear zones, faults. The Great Himalaya, we have more crystalline rocks, relatively stronger, but near the thrusts and faults, graphitic schists can occur locally, generally higher grade metamorphics, granite gneisses, intrusions. The two main thrusts we have, which we talk, is the main boundary fault between Shivaliks and Lesser Himalayas, and main central thrust between the Lesser Himalayas and the Great Himalayas. Uh, I would request everybody to mute their mics because a lot of disturbance is coming. This list is just indicative. It doesn't mean that only this rocks are coming or only this kind of faults are. It's just for the sake of understanding. The past experiences moving from northwest to southeast, I have taken 4 projects: Kishan Ganga project, Dulhasti project, Parvati hydroelectric project stage 2, and Vishnugarh Tapovan project of NTPC. These are the experiences which we have. First, let us look into what happened in these projects before deciding upon the methodology for identifying risk and finding solutions. It will come automatically after we learn these experiences. Dulhasti project, as you all know, is one of the very early projects in the Himalayas. The first TBM to be deployed there. The project had a 10.6 kilometer long HRT. It was planned to bore a length of approximately 7 kilometers using open type hard rock TBM, as there was no intermediate edit. The work was started on turnkey basis in 1989. The work was stopped in 1992 and restarted in 1997 and finally could be commissioned in 2007. HRT to be executed from 2 ends. There is a huge Kistawar plateau which is crossing. You don't have any drainage or a deep nala to find an edit. A Robbins TBM from upstream end was deployed in quartzitic phyllite for an envisaged length. We targeted 6.75 exactly at the time. And the originally was adopted from the other side for 3.85 kilometers. Average progress of only approximately 40 meters per month could be achieved. Maximum progress, though, in 1 month was 176 meters. TBM could bore 2.8 kilometers and got stuck under flowing conditions. Balance 4 kilometers was completed by DBM method from upstream side and 1.5 kilometers from downstream side, also by DBM. The Kishtawar Plateau, a lot of phyllites appear on the surface map, but once when you see the section, you will find that there is a lot of quartzite. A lot of senior geologists in this group have worked over there. They know how hard that quartzite is. What was the overburden in that plateau and how the tunnel was rerouted to avoid that low cover zone. You can see a lot of quartzite over there and very little phyllite. There were frequent shear zones, water coming under high hydrostatic head, peat discharge as high as 1200 LPS, flowing conditions, pieces of quartzite flowing out with high discharge of water. Such type of episodes occur at an interval of half a kilometer. Tunneling in phyllites was relatively faster. rock stress issues, and ventilation problems as in all long tunnels. We come to the next example, Kishanganga project. This is a long tunnel, once again diverting water from Gurez Valley to Bandipur to the Muller Lake. A very ambitious project. People said at that time when it was planned, a maximum cover of more than a kilometer at Razdan Pass. Most of the area is always snowbound. And 11-kilometer tunnel length had a high cover, the one edit, and another near the search shaft. As long as 14.75 kilometer length was planned by TBM for the search shaft and remaining 8.5 by drill and blast from the intake side and the other edit. Kashmir geology, as you know, is complex. The Indus suture occurring towards northeast. Panjal thrust is in southwest Kashmir. Main boundary fault more on the outer side. Dam and underground powerhouse were placed in basaltic Panjal volcanics. HRT in a gamut of rock types belonging to Madhumati group. It's flanked on either side by Panjal volcanics. Although it was very difficult to go due to the law and order situation over there and the topography, still map was prepared. Panjal volcanics, siltstone, metasiltstone, sandstone, metasedimentary formations were highly joined. A section, a geological section of the HRT does show, as I said, metasedimentary is in the middle, flanked by Panjal volcanics on either side. Anticipated rock class, rock mass classification is 15% class 2, majority of class 3, and 4 and 5, 20%. With the experience of Dulhasti and Parvati, NHPC was aware about the problems of high stress, squeezing ground conditions, faults, shear zones, high ingress of water. These were communicated in the contract. Contractor also did his own study, instrumentation, probing ahead of phase, pre-grouting, and a provision of overcutting, especially provision of relief holes to reduce stresses, ice plant for high temperatures, probe holes. All these provisions were there in the TBM. The TBM selected was a double shield universal manufactured by Mr. Selly of Italy. They only partnered with HCC to run the machine at site also. The machine allowed constant production in wide range of rock and support conditions, allowed easy erection of concrete segment. Excavation started in May 2011 from 266 meter long shear shaft edit. Initially hard and compact jointed rocks. Panjal volcanics were encountered for 1400 meters. Then at certain RDs there was moderately to highly jointed rock mass class 4 and class 5. At the contact of Panjal volcanics and Madhumati group, there were problems. There were carbonaceous phyllites also. Chemical grouting was used and conventional supports, apart from the segmental lining. The transition between Panjal volcanics and meta basics of track bulk formation and meta sedimentaries, adverse geological conditions were encountered for 40 meters. There was some water also, and tunneling was continued. The TBM was almost in danger of getting stuck there. And they did made an opening in the crown portion and went in front and then supported it by certain ribs and wooden spacers. And the TBM came out of that very most difficult zone in that tunnel. As I said, when there is a success in the TBM, and there is a spectacular success. 14.7 kilometers tunnel stood completed. In June 2014, it was completed. Average progress is phenomenal, 400 meters per month. Maximum progress touched 812 meters per month in November 2012. And maximum progress in a day is 43 meters. Even in the end, there was a sustained progress of 300, 400 meters. Picture from Gurez Valley, Sharshaft area, picture of TBM and the line tunnel. You have the hexagonal segments. Great success. TBM at Kishanganga, double shielded TBM. Now we come to the most difficult tunnel, I would say, one of the most difficult tunnels of India, the HRT of Parvati. But before that, in the same project, we had an inclined pressure shaft, 1500 meter long, in which there was a phenomenal success, the world record, in the same project. Total there is a more than 50 kilometers of long tunneling in Parvati, added to the HRT or the edits, the approaches to 3 large desilting chambers excavated. All those things took place. But what is remembered in Parvati is only the balanced 2 kilometer HRT by TBM. This tunnel is in Rampur group, mainly in Manikaran formation. As we know, on both sides bounded by thrust. We also have a local thrust between Manikaran and Banjar volcanics, which we call the Rela thrust, which we intercepted in the tunnel near the Sarcha, and then towards the south, the Shivaliks and all. I am talking about the successful boring of inclined pressure shafts in the beginning, 1500 meter long, 30-degree upward angle. I particularly wrote this because in world first time a TBM was being tried at a 30-degree upward angle. This was the bottom edit to pressure shaft, which we call. We went there, we made this V junction, all in meta basics. Then we reached here. We made a small chamber here. The TBM was brought. It was assembled. It went up like that. It came out from this edit, and from a road, it came back again and went to the other tunnel and completed this also. A great success story there. The details of TBM. Mitsubishi TBM, telescopic double shielded, operated by Jagger Sailing. Boring diameter 4.8, 17 inches disc cutters, 32 disc, maximum thrust 250 kilonewton. This is what typical and mostly in other TBMs also, as you can see. And precast lining with the peak gravel, the grouting there, provisions of advanced probing also. Metabasic and chloritic schist bands A lot of investigation, 5 drill holes over there, and we had a drift in the bottom and in the top also. We could develop this section. This is the picture of the inclined TBM being assembled in that hole I told you at the bottom of the inside the pressure shaft. Mean pressure shafts of Parvati 2 at 30 degrees, world's steepest with TBM. Left pressure shaft was completed in 179 excavation days. Right pressure shaft was excavated within a record period of 109 excavation days, only with a performance of 14 meters per day. No major problems were reported during the excavation. Thus, the decision to opt for a double shielded TBM in case of inclined pressure shaft was correct. Let me tell you that NHPC after this was under great pressure in some of the projects to deploy such type of inclined TBMs. But because the geological conditions were not so favorable in those projects, we did not agree to that. This is about the left pressure shaft and the right pressure shaft, which was much faster after this experience. Now coming to the headrest tunnel, I'll have to be a little bit fast. Length 31 kilometers, diameter 6.8, design discharge 116, superincumbent went as high as over 1500 meters. Length to be excavated by DBM. All the length apart from the 9.9 kilometers by TBM was by DBM, 5 edits. You can see this is the between this edit 1 and edit 2 there is a steep water divide with a very high ridge. There is a reserve forest. A lot of effort was made to locate a edit from here, from going in from Kasol. But there was restrictions in forest, the edit length was too long. So NHPC deploy a TBM here going in from edit 2. This is the picture of the edit before it's taken inside. Details of TBM specifications at Les Copco. This was a refurbished machine. It was used for a smaller dia earlier. It was then modified for this diameter. It has a maximum thrust, 25,000, although the allowable was only 13,800. 52 cutters, and per cutter also it is about 256 kilonewton. The geological section did indicate a majority of Manikkaran quartzite. This is Bandal granite for you and carbonaceous, and then the Kullu group, biotite schist. Even this zone of 1 kilometer was only 400 meters. There was a tectonic wedge of Manikkaran quartzite from this side. It came up till here, and from this side the TBM was proceeding. The story is, initially the tunneling was carried out very smoothly in 3.5 kilometers of granite gneiss. The moment it started entering into Manikkaran quartzite, things started to be difficult. The frequent change of cutters only after boring after 575 meters in Manikkaran quartzite. During a routine probing, a peculiar brick colored such material came. Second probe hole was done. It got choked. And then the third probe hole was done in an incline by a smaller Hilti machine where just water started flowing. And the flow increased to 11,000 liters per minute with a lot of silt. It did start to go to 7,000 LPM. and the next day the situation got out of control, and unabated flow of water with a 9,000 cubic meter of fine silt and sand inundated the tunnel for about 2 kilometers, and the TBM got buried over there. This was the first case where a shear zone was met with a water coming as high as 40 bars from a very small drill hole. Probe drilling was undertaken. We did introduce a new technique, geophysical investigation, tunnel seismic prediction. They indicated poor ground ahead of the face. By a series of probe holes were done, 4 core drill holes were done. There were problems in the holes also. And after cleaning all the silt and sand, the TBM was refurbished, cleaned, re-oiled. It took, all these things took a considerable time. And meanwhile, NHPC appointed a foreign consultant for treatment of the shear zone. The ground consolidation ahead of the phase at the time first meant that the area around the machine itself, because we had to make a bypass, we would strengthen the area, then how to drill these holes. It was many new things we came to know. There's a very portable Lomesa drilling machine which was used for strengthening the mass around. The TBM retracted back, and then further drilling and consolidation around the tunnel. Canopies, the grout canopies like that, all along the tunnel, 5 canopies. And I cannot show all these details. I have a lot of material, but due to the time constraint, I'm going very quickly. These are the probe holes. Treatment of the shear zone was carried out, 39 meters. Ahead of this shear zone was cautiously excavated. Then after reaching 490, 4095, once again probe drilling was undertaken. This is the kind of weak zone after in between the first shear zone and the second shear zone. Once again silt-laden water came, and just some glimpses of the type of outflow, water ingress, and the geologists did come up with another shear zone at RD 4118. So meanwhile the contract was terminated, retendering was done, and a JV got awarded in August 13. NHPC was careful this time. It did some survey, resurvey by remote sensing, and then they asked geologists how many fault zones are there, how many shear zones are there. Tell us. All the engineers wanted this information. So NHPC at that time did used satellite imageries and came up with this kind of lineaments. Meanwhile, then the 4118 shear zone had to be treated. Again, a consultant was appointed. This is a very simple depiction of the elaborate treatment which was done. I'm showing it in a very easy diagram, in a 3D view. The side tunnel and then the treatment of the difficult zone from the side tunnel also, from every possible place. Another consultant was appointed. He told that there are local faults also, but then NHPC did strengthen this, confirmed by seismic tomography, TST, probe drilling, and finally boldly went ahead. This is the box which is showing the disturbed zone from the probing. This is the view of side tunnel, chemical grouting, an actual shear zone which was thought to be like this, and it was slightly lesser than that. I was there at Parvati. I've given you just a glimpse. This is the McNally plate. This is the crown Over the crown, another tunnel forms. This is the type of overbreak which we experienced. These joints are parallel to tunnel abutment, not a very big shear zone. These are closely spaced uh, joints, uh, can say a brittle shear mass, and nothing like squeezing here, but then it falls down. And look at that backfilling by concrete. Still this portion has to be backfilled. Such type of difficulties. Now is it possible to project this zone 1000 meter on ground and get it accurately? Summing up, Parvati cutter consumption, I'll come to that subsequently. Shear zones, fracture zones, water ingress, stress-induced failures, I would say, rather than rock busting, squeezing rock, contractual issue. There were instances of moderate rock busting also, mild to moderate, but not a very violent thing like something like a bomb, you know. But there was a very difficult for people to work there. But then after some time, they got bold enough, they got used to these things. They took precautions by ring beams, you know, by channel support, by putting wire mesh, and that is how proceed cautiously. Uh, the last example, Tapovan Vishnugad, very briefly, 11-kilometer long HRT. There also a double shielded TBM machine is there. There were two trapping events. I am told once again the tunnel they are going with a bypass tunnel and treating those zones. Now coming to summing up our experiences. You will be surprised to know that even now when we do work for consultancy, we're going at many places, we are seeing that the basic condition of a tunnel, putting in the rock with a sufficient rock cover, is lacking in some of the products. Why this is happening, I don't understand. The engineering considerations are so much overriding that you want to put tunnel in an overburden and not just shift it 20 meters inside. Are the engineering considerations so important? I don't think so. These things have to be seen at the DPR stage itself. Lithological variations. The geologist must come up with a reliable report about the amount of granite, for example, amount of schist, amount of slate, which are expected in the tunnel. Rock strength and observativeness. Parvati quartzite is very typical. It involves frequent change of cutters. During the investigation, the compressive strength was as high as 260 MPa in one of the sample. At site, we found 181 MPa. Some of the samples, but it fails in the concrete aggregate. The Los Angeles aberration is more than 70%. This is a peculiar thing which has happened, and it gets crushed into a fine silt which comes out with the water, particularly near the shear zones. Some of the rock is also getting crushed. High stresses. We need to study the geologic structure fully of that area. What is the stress pattern? What type of fault mechanism is there? That all has a bearing on the rock mechanic properties and engineering behavior of rock, particularly in deep-seated tunnels. Please appreciate this. Blocky and jointed rock masses are hell of a problem in TBMs. Fragmentation in rock. How the rock fragments by crushing. Is it coming in the conveyor belt to be able to be so that the mucking out is easier? What are the environmental issues? Use of chemical grouts, risk sharing in contract. Only a one line I have written, but it's a huge subject. I'll come subsequently. risk matrix, for example, people should learn to say no to some of the alignments. If the consequence is disastrous, for example, and the frequency is very unlikely, that risk is unacceptable. Severe, serious, unacceptable risk. Likely also if the consequences are disastrous, it is unacceptable. You have to find a solution to it. Either change your alignment or regardless of the cost. You can do anything today. Technology is so advanced. I can consolidate a loose sand if you give me time and money. I can do it and I can make a tunnel through it. People have been doing that. But what is the cost of that exercise? That risk mitigation has to be there. There are some acceptable risks and there are some negligible risks also. These are guidelines taken from International Tunneling Association, the guidelines from risk management. You can refer to that document. Geophysical explorations. People have been talking about airborne geophysics. Some of the companies are doing it, electromagnetic service. They say we can fly over your alignment and we can give a list of fracture zones which are expected. You can correlate that with your remote sensing study. A lot of high resolution imageries are now available. You can do it. Tunnel seismic prediction is 3D now, it has advanced. Some of the TBM manufacturers have put in as a tool in their machines. Don't be adverse to any type of technique. You could do gravity surveys, it was done in Dulasti. Rock cover I talk, what is sufficient? Whether 3D or 10D? Well, it depends on the rock quality. Topographic, geologic surveys, you all know that. High resolution imageries, physical traverses in the area. Now we have drone mapping also. Luckily, now we are fortunate. Without going to an area, we could fly very close and get some pictures.
Sorry for disturbing, Imran
Collection
Sorry for disturbing.
Collection, yeah.
We have
I am concluding.
10 minutes, so if you can.
Yeah, I am concluding the list of rock mechanic tests. There is a long list. Most of them indicate the abrasiveness and hardness of the rock. The cutters is a picture of usage of tunnel, comparison between Manikkaran quartzite and the inclined TBM. What is the international boring, how much percent it should be? You can compare this. Rock stresses, I have already told you. Is it the folding in the rock which is causing a stress, or it is due to faulting, or it is due to high cover, or is it due to only topography? All these analyses have to be done. Provision of contract for treatment of want to use TBM in the Himalayas, grouting has to be there as an integral part of tunnel. For different geologic materials, you could range from cement to acrylamide. You have ultrafine, microfine cements in between. You have to have a complete knowledge of the rock and the grouting technique and the material which is to be used. TBMs are now manufactured in many types and are more versatile. We have gripper TBMs, we have single beam TBMs, we have single shield, double shield. An independent expert will advise you regarding TBM is a big investment and methodology cannot be changed at a later date without incurring huge setbacks in time and cost, so much so that the project itself may become unfeasible. Please investigate, test, plan and proceed. Thank you very much for your attention.
Thank you, Imran ji. Thank you very much. That has been a lovely lecture. and your final sermon is appreciable, that it is a complicated matter, and you need an independent consultant who knows the job to decide for you what TBM is to be used depending on the ground conditions and other things. Anyway, thank you so much. It has been very revealing presentation and enjoyable as always. And Varun, कुछ queries हैं क्या उसमें? Varun, are you there?
Yes, sir. Yes, sir.
Queries हैं उधर? क्या
Yes,
drop
sir.
में?
Yes, sir. Screen share कर रहा हूँ.
शेयर कर लो. अभी
Okay, sir.
ऐसा इमरान जी ऐसा करेंगे, अभी 8 मिनट्स हैं हमारे पास, तो अगर कंप्लीट हो जाएगा तो ठीक है, अदरवाइज वी विल I mean send the queries across to you by mail, and we will share it by mail.
Yeah.
The participant.
Yeah. I can see one question by Arindam Chakravarti. It is commonly said that Parvati 2 project is suffering due to geological surprises. However, I feel it's not geological issue but due to improper selection. Please provide. Yeah, there is a lot of discussion on this. We have had plenty of discussion. What kind of machine? The machine is very strong, Parvati, but it's an old machine and it's a refurbished machine. Probably if there was more space, we could have done more justice to the treatment, particularly removal of silt from down below. These things are there.
थोड़ा बड़ा कर दो उसको.
Are geologists to blame for all this? No, we are not blaming anybody. We are trying to understand why the double shielded machine has succeeded in Kishanganga, why it is not succeeding so much in Tapovan Vishnugar. We could have said put a double shield machine and your tunnel will be made. In one project it was successful. In Parvati itself, the same team, the same group of people were managing. One was a phenomenal success, another is not so successful. What I feel is a lot of thought has to be given for two things. The first thing is hardness and abrasivity of the rock. No contractor can afford to have a cutter change at every 0.88 meter, one cutter, as it was there in Parvati, which came down to 0.4 meters per cutter. The cutter is a heavy thing. It has to be taken inside. It has to be changed. It takes a time. And if all the time, if they are changing the cutters, then where is the time for boring? And second thing, once the penetration rate is slow, then the advance is slow. Behind your support system is coming. That also becomes very slow, you know. So the rock, unsupported rock, remains unsupported for a very long time. I said this, if you want TBM to succeed in a fractured rock, in a water bearing zone, pre-grouting has to be an integral part of this machine. You have to do pre-strengthening of the media, because in the cutter head and at the face, the rock has to stand unsupported. In the drill and blast, what we do, we go to the face, we do grouting in the face. Here the grouting is being done in the periphery only. That's how we are trying to bring a extremely poor rock to a fairly good rock condition. We have to have that much of improvement for the TBM to pass smoothly. If not fair, at least we have to bring it to the poor condition from extremely poor. So that much of pre-strengthening is required. That can be done either by pre-grouting or by forepoling. Forepoling is successful in a jointed rock. Once again, there is a angle restriction in putting the forepoles. For putting support only in the crown, we have to put it in the walls also. As you all know, the most weak rocks require support even in the invert. So, is it possible? Is it possible to do it in advance before reaching that point for boring? That is the question at hand. If you are able to solve that, then you can proceed cautiously. Probe drilling, investigation ahead of phase, all have to be a part and parcel. But you need to have some sort of geological model. You cannot say, the geologists cannot say you probe 100% and then, well, they are doing probing almost at the 100%. But then, as I said, in the risk matrix, some things are unacceptable. If you are getting a 10-meter wide shear zone after every 100 meters, how can you make that tunnel economical? The whole question is economy and time here. So there should be a methodology which is fast to implement, and also you are able to spend that much of money. All these investigations, and then the stresses, this quartzite, I'm sure, if it is 200 meters depth, this will be much more stable than what it is now. I can easily tackle it under a cover of 200 meters. But mind you, I am working under a 1000 meter of cover, where the stress situation is entirely different. The wedges which are stable under a depth of 200 meters are not that much stable under 1000 meters. The same wedges, the same joint system. So what you are picking up the data on the surface has to be transferred to that depth, and then the conditions visualized, because that is what you are actually going to do. In my opinion, we should not try to apply rock mass classification in true sense. We can have only some indirect considerations of advance rate, vis-à-vis, rock strength, abrasivity, etc. There are references in literature where they have tried to derive some characterization of rock mass by observing rock mass through inspection windows and rock cutting. But it would be too risky to interpret rock mass classification from there. It's a good question.
I will just not an interruption. We are taking a very, rare deviation from our practice. The time is over, but I think people are interested, so we can go ahead with the question answer session. Till it lasts. I think our participants will come that. Please.
Yeah, what is coming in front of me, I am reading it and I'll try to answer as quickly as possible.
There is something has shared on the screen. The queries are shared on the screen in that order in which they came. Can you see these queries on the screen?
Yeah, I am seeing the question. In my opinion, we should not try to apply rock mass classification in true sense. We can have only indirect correlations. This is by VP Data 2018 guest. There are references in literature where they have tried to derive some characterization of rock mass by observing rock mass through inspection windows, rock cuttings, but it would be too risky to interpret rock mass classification from that. In an open TBM, now we call it even a beam TBM or a gripper TBM, which is open. In that, the rock mass is visible behind the cutter head. You could do a classification, you could apply support. But in a shielded TBM, as he has rightly pointed out, there is a very small inspection window. From there, you cannot get an idea of the rock, entire rock mass classification. People have come out with something as a thrust index, depending on the thrust, penetration, time taken, revolution per minute. They are trying to correlate the mechanical performance of the machine with the rock mass, well, those are all indirect things. The best thing is probe drilling and try to take out the core. You can do some classification in that. Yeah, Mr. Pandey has asked that. Then in a double shield TBM, is it possible to carry out rock mass characterization as spaces were not properly? No, it is not possible. There is only a small window. You have to rely on probe drilling and other methods. Beam is also a technology which has come. Actually, I was a part of a task force which NHPC had made in 2017 to study the various methods and how we can proceed ahead. At that time, we came across this beam technology, which is fixed on the machine itself. TSP is slightly different. Terrain is most important factor. Manvendra Dayal guessed terrain is most important factor, like in case of quadratic rock is playing a vital role for excavation. Very important. Uh, uh, One of the factors in case of inclined TBM and in case of Kishamganga has been the strength of the rock. We have to admit that. It's a moderately strong rock in which the tunneling is faster and the support is coming. So rock has got a little time to move. But then in high cover regions there is a danger of squeezing in such a type of media. So those things have to be taken into consideration. Quartzite indeed is a very difficult medium. Even in drill and blast, the contractors are not happy with quartzite because it means a lot of bit changes even in the normal drilling for blast holes. And quartzite is notorious for a sudden fracture and water under high head. Mr. Sumit, which geophysical method should we select to be installed on TBM or a continuous assessment during excavation? I have gone through, you can also go through Herricknet, Robbins. They all have very beautiful videos on their latest TBMs. They are suggesting TSP, थोड़ा सा नाम चेंज कर देते हैं. Method वही है, principle of blasting and then taking small blast and then recording the P and S waves and trying to interpret the media ahead.
So I think Imran ji, can we
Yes.
now call it a day, and we will just compile the
other questions can be.
We'll compile the queries and send it across to you, and you can give the replies, and we will share it with them, and we will check. I mean, we will assess if the queries are too many, and it will take some time. So we can even plan another session with you only for question and answer and some other thing. Okay, will that be all right?
All right. Thank you very much.
Thank you very much. I mean, your lecture has created lots of response, and so many queries are still there. So let's see. Let us assess how many queries are there left. We will share it with you, and then we can go ahead with it. So thank you once again. Thank you for your lecture. And I think it would be more befitting that Dr. Dhawan concludes today's session.
Thank you very much, Mr. Imran and Mr. Deva. It was a very informative lecture, and I really liked your concluding line when you said, investigate, plan, and proceed. In my opinion, we lack in both, particularly we not only for TBM tunnels, I think for any Himalayan hydropower tunnels, I would say that we need to improve our level of investigations. We leave a lot of things to God's will. भगवान भरोसे, भगवान सब अच्छा करेंगे, जब आएगा तो देखेंगे. I think our preparedness to encounter the enemy is lacking. First of all, we do not carefully identify the enemies which we are going to encounter during the course of tunneling. And even if we know, because it is very difficult to tell the place where the enemy will be there, but certainly many times geologists are able to forecast that such kind of situation or extraordinary geological situation may be encountered. So the planning, I'll not go into the details, but planning is lacking, and we, from today's lecture, we can conclude that we need to improve our level of investigations and also the planning for meeting those challenges. Imran Sayeed has given a very, very concise summary of all the important hydropower tunnels which are being done or have been done by TBM. In such a short time, he has done a commendable job. And to encourage Mr. Said, I find that there are so many senior persons which I can see they are there in today's gathering. And Mr. H.L. Arora Sahib is there from THDC. He was former Director Technical. Mr. Ahmad is there from Dubai. Mr. Yamuna Singh Sahib is there from AMD. Mr. Rajpal Singh Sahib is there. He was former Joint Director in CSMRS. Mr. Prabhash Pandey, our old friend, Additional Director General, retired from GSI. Then Mr. Kanwar Singh, Director Civil from SJVN. Mr. Lomas, my own predecessor, the former CMD of MECL, is also there. Mr. Binay Mishra is there. Mr. N.K. Mathur is there. Mr. A.K. Mehrotra from MECL is there. Mr. Gajendra Pratap Singh is there. So many senior people have joined together. And please excuse me if I have left anybody's name, because many times, you know, I try to identify you either through your faces or through your email IDs. And I may be excused if I have left some name. But please keep coming, keep blessing our programs. And I would request all of you to please visit our YouTube channel. We will upload this lecture on the YouTube channel. There is a channel in name of Academy. And you can please subscribe also, so that whenever we upload a new video, you will get a notification. So thank you very much. And back to Mr. Deva, please.
Thank you very much, Dhawan Sahab. Thank you very much once again, Imran Sayeed ji. And thank you very much, our distinguished guests and participants. And we should be back next month, first Saturday or second Saturday, with another edition, the lucky number 7 of the Academy. So see you next month. Thank you very much.
Oh,
and be back with us. Thank you so much. Have a good evening.
Thank you,
Thank you, sir.
Thank you, sir.
Let us give a big hand to Mr. Imran.
Thank you, sir.
Thank you. Namaskar.
Namaskar, Dhawan Sahab.